All right, so let me draw a diagram. So let's say we have a particle following some trajectory in 3D space. So currently the particle is at some point with position vector r, and is moving with some velocity v. So you can find the velocity as the derivative of the position vector. So the velocity is equal to the limit as h approaches 0 of the position vector at time t plus h minus the position vector at time t divided by h. And you can see that the velocity vector is tangent to the trajectory. The acceleration, same idea. It's the limit as h approaches 0 of the velocity at time t plus h minus the velocity at time t divided by h. And kind of the last precursor that you need to know for what we're going to cover is Newton's second law. And Newton's second law states that the force vector is equal to mass times the acceleration vector. Now, mass is just some scalar, so both of these are going to be pointing in the same direction. So the force vector and the acceleration vector are parallel. So what does that mean? That means if I exert a force on this particle, let's say that's the force on the particle, then the acceleration is also going to be in the same direction as the force. Okay, so now we kind of understand and we've defined what a position vector, velocity vector, and an acceleration vector is. So typically when we look at particles moving in 3D, we may want to control them and kind of move them into specific places. And to do something like that, we use something called a control system. So what is a control system? A control system is basically a system used to regulate or track a specific quantity. So for example, this can be temperature. You want to control the temperature in a room, use the thermostat. That basically has some control system involved. What else? You can control voltage, you can control position, orientation. There's an entire plethora of different systems that implement some form of control. So back in 2019, I was doing a 4th year NSci course, ECE557, and that is a controller. That's a course on linear control theory. And one of our projects was to control an inverted pendulum on a cart. So basically, you can imagine you have this pendulum that is free to move on this cart, and you kind of have to balance it in the upright position. So if it starts leaning to one side, you move the cart to kind of put it back in place. And we had like in-lab sessions over there, and half of the time we would actually do stuff, and the other half we would just mess around and be taking videos with our phones and stuff. So I went digging through my Snapchat memories, and I found some old videos of the pendulum I could show. So let me swap on over to that. So here it is. So this blue stick over here is the actual pendulum, and this cart that moves along this track is basically used to keep this upright. And that's my lab mate.
So you can see that he nudges the pendulum and the cart kind of moves in a way to still keep it upright. I'll run that again. And control systems are really important because sometimes you don't know the exact dynamics of the system. So we designed the pendulum to work with assuming there's no mass on top. You can see that even when I put my wallet on top of the pendulum, it still kind of understands what it has to do. So there's some robustness to the actual system, right? Sometimes what happens when you don't design your control system to work with really large deviations from the desired position, this is what happens. So this is where we smack the pendulum a bit too hard and it can't recover. So those are the pendulum videos that I wanted to share. Right, okay, so let's discuss about the system that we're going to try and control today. So we have, I'm going to call it a drone just because this is kind of like we're trying to do some positional control for a drone. So let's say here's the origin, here's our drone, it has mass m, it has a position vector r and some velocity vector v. And we can say that the drone can produce a force in any direction that we want. So the drone can produce any directional force, and we'll call that FCTL for control force. So now let's talk about some forces on the system. So when you have a drone flying around, there's two major forces that we need to care about. There's a gravitational force, which I'll call F sub G, and the gravitational force is equal to 0, 0, and minus mg. So it has a magnitude of mg, which is the weight, and it's directed along the negative z-axis. So that's the gravitational force on the system. Now the aerodynamic force, or the drag, so F drag, well, drag is proportional to the speed of the drone squared. So it's proportional to the square of the speed, and it's in the direction opposite to the velocity. So if the drone is flying forward, the drag is going to be in the backward direction. So when I want to just have the direction of the velocity vector and ensure that it has a magnitude of 1, we call that a unit vector. So, and unit vectors are ones that have hats on top of them. So v hat is equal to, I can just take my velocity vector and divide it by its magnitude. So when I divide it by its magnitude, it scales the vector to have a magnitude of 1, pointing in the direction of the velocity vector. And now I can write out my aerodynamic drag. So my aerodynamic drag is equal to the coefficient of drag is just some quantity, and then the square of the speed, so that's the magnitude of the velocity squared, and it's in the direction that is opposite to the velocity, so in the negative v hat direction. And I guess I can just substitute our definitions then. So minus cd speed squared, and this is equal to velocity vector divided by the magnitude, and this is squared, that's 1 power, so I can cancel those out, so I get minus cd speed times the velocity vector. So that is our aerodynamic drag force. Let's see, what else? The way that we're going to be incrementing our position and our velocity variables in time, let's talk about that. So we're going to be doing Euler integration. And what that means is that the position vector in the k plus 1 time step is equal to the position vector in the kth time step plus our derivative. So our velocity vector in the k time step times delta t. And then similarly, the velocity in the k plus 1th time step is the velocity in the k plus the acceleration times delta t. And we can use Newton's second law to substitute with the acceleration. So you get vk plus f over m times delta t. And F over here being the net force on the system. So after we add our control force, our gravity force, and our drag force all together. Another quantity that we will track that won't make sense right now, but will eventually, is the integral of, what does CD stand? CD just stands for coefficient of drag. Coefficient of drag. It's just some arbitrary quantity that scales our drag vector, right? So if you want really big drag, we just make CD really big. If you want zero drag, we just put CD equals 0. It's just some constant. But yeah, so the last quantity that I want to track is the integral of the position vector with respect to time. And I'll tell you why later. But the integral of the position vector in the k plus 1 time step, so this is basically going from 0 to t k plus 1, is equal to the position vector integral from the kth time step plus position vector times delta t. And the intuition for this is that, let's say I have so this integral basically represents the area under the curve from 0 to t sub k. And then this r delta t is basically just an approximation of the area over in this strip over here. So when I add them up together, I get the integral from 0 to t sub k plus 1. So we're also going to be tracking this integral. And I think in my code, I call this quantity I, because I is the integral. Okay, perfect. So now let's hop on over to MATLAB and start coding this up. So let's see. I'll start out by creating a simulation time vector. Probably seen me do this a bunch of times if you've been in some previous tutorials. So how long I want my simulation to run for. So 100 seconds. I'm taking time steps of 0.001 seconds. And this t vector over here is something like 0, 0.001, 002, 003, and so on, all the way up to 100 seconds. And then I have all these initial conditions of my system. So for now, let's just say the initial position and velocity are all the zeros. So the drone starts out at the origin, and it starts out at rest because there's no initial velocity. It has a weight of 0.75 kilograms, and gravity is 9.81. Or drag coefficient, I just put 0.05. Controller gains, we'll talk about that later. Okay. So what RD, VD, and AD are basically the desired position of the system. So if I want the drone to move to the origin, basically I set RD equal to 0. So this is the desired X coordinate, desired Y coordinate, and desired Z coordinate. And you have to do this for every single time step. In this case, since basically our desired position is just zeros, so we differentiate that, you get all zeros again, you differentiate that again, you get all zeros again. So this is the desired position, the desired velocity, and the desired acceleration of the system.
everything over here is basically me just saving my data into all of these different variables. So R is going to contain my positions for every time step. V is going to contain all my velocities. FG is going to contain all the gravitational forces, aerodynamic forces, control forces, and then this would be like net forces on the system. And since we have the initial position and the initial velocity of the system, I can basically put those into my array. So if I run this, you see that here's the positions of the system. Maybe if I just change this to something like 1, 2, 3, if I run this, you can see that 1, 2, 3 shows up over here. So at t equals 0, the position is 1, 2, 3, and then these other ones will fill out using a for loop. Let's keep this here. What else? I is that integral term. So since we're integrating a 3-dimensional vector, then this integral is also going to be a vector with 3 dimensions. And I guess the next is just actually computing. So we're going to be running a for loop, going through all of the time array. And so this is our thing for the position. So the position vector at the next time step is equal to the position vector at the previous time step, plus the velocity times delta t. The integral is equal to the integral from the previous time step plus, I guess for now, yeah, so plus the error in the position times delta t. My gravitational force is 0, 0 minus mg. My aerodynamic force is, for now, let me just remove my control force since we're just going to do stuff without control. So my aerodynamic force is minus my coefficient of drag and then the speed and then multiplied by the velocity vector. And then the net force on the system is the sum of the gravitational force, the drag, and yeah, just the drag for now. And then once I have the net force on the system, I can say that the velocity in the next time step is velocity in the previous time step plus force over mass, which is acceleration, times delta t. And I can also just copy this code that just plots the positions and the velocities in all directions. So let me run this. Let's see. Let's actually, okay, make some predictions what happens if we have no drag. So the drone starts out at the origin and you basically just let it go. So we see that the drone starts accelerating in the negative z direction, right? Because gravity. And in 100 seconds, it reaches a speed of around 980 meters per second, which makes sense because g is 9.81, and our z position is following a quadratic because, well, quadratic is an integral of the linear velocity profile over here. So that's all working just fine. So now make some more predictions as to what will happen when I turn on the drag coefficient. So the object is in free fall with some aerodynamic drag being applied to it. Or emails. So on this. Okay, something else is happening to the velocity. The velocity is decreasing initially until it reaches a speed at which it just becomes constant. So any guesses as to why the velocity stops increasing after a certain speed? There's a very popular term for this phenomenon. Terminal velocity, yeah. So let me just kind of demonstrate what terminal velocity is.
So as the object is falling down, its speed starts increasing. So let's say here's our object, there's a weight, there's a force mg pulling it down, and there's a force in the opposite direction with magnitude cd times the velocity squared. So as the velocity starts to increase, this force starts becoming bigger and bigger until the point where both of these are equal to each other. So where the gravitational force is equal to the aerodynamic drag. So at that point, the net force of the system is zero and the system stops accelerating downwards. We can actually calculate this terminal velocity. So you have CD V terminal squared equals mg. So therefore, the terminal velocity is equal to square root mg over CD. And I think the values we had was CD equals 0.05 and m equals 0.75. So if I plug those in, square root of 0.75 times 9.81 divided by 0.05, that gives me a terminal velocity of 12.13 meters per second. Now let's check that with what we obtained. And you can see that the speed stops accelerating at 12.13 meters per second, exactly like how we predicted. So the gravity is working just fine in our simulation, and the aerodynamic drag is also working just fine in our simulation. So now let's actually talk about control. So the technique of control that we're going to be implementing today is feedback control. Feedback control is when you use the state of the system to determine what your control input would be. So this is feedback control. And the specific form of feedback control that we're going to be implementing is PID control. And each one of these letters means something. So P stands for proportional. So what is proportional control? So let's draw this. So let's say we have some particle that has a position vector r. Well, the proportional feedback commands a force that is in the opposite direction of this. So Fp is equal to minus Kp times r, where Kp is greater than 0, and this is called our proportional gain. So if the particle was at that position, then F sub p is going to look like some force like this. So you have F sub p. So it's going to be pointing back towards the origin in this case. And you've actually seen this before. So kind of like if you wanted to imagine what happens when you implement proportional control to your system, it's the exact same idea as a spring mass system over here. So let's say the mass started out at this position and you pulled it with some displacement delta x, then the spring force is equal to minus k delta x, right? And this is basically the exact same thing you have over here. Ff and then minus k. So in this case, it's a proportional gain is working the same way as the stiffness of the spring, and this r vector is the same thing as the delta x that you're pulling on. So this proportional control
basically works exactly like a spring, where it'll try and pull the thing back to the origin. Okay, so what happens if we just have a spring and there's no damping in the system? Well, the system's just going to oscillate forever and never actually converge to zero. It's going to just keep bouncing around. So that's where derivative control comes in, and that's what D stands for. So D is derivative control. So let's say you have a particle with some velocity, then what derivative control will command is a force in the opposite direction of the velocity. So this is equal to minus kd of the velocity. And kd is also greater than zero, and this is our derivative gain. So this is basically the force F sub d. So what does this do? Well, this Fd always creates a force that is in the opposite direction of the velocity. So it always decreases the speed of the system over time. In a way, this basically acts as your damping in the system because it's always resisting that velocity vector. So this slows your system down. And adds damping. And I is integral control, and we'll talk about that afterwards. So let's implement proportional and derivative control. So without the integral part, instead of PID control, it's called just PD control. So we'll start by implementing PD control and then add I to that. So here are my controller gains, so that KP, KD, and KI. I can just put that over here. And since we're not using any integral stuff, so I'll just set KI equals to 0. I can put my F control back in. So this is basically the array where I'm saving all my control forces. And this is where I'm calculating my control forces. So control forces equals minus Kp times the error in the position. So that's R minus R desired. And then minus Kd times the error in the velocity, which is my current velocity minus the desired velocity. And since we're not using any integral stuff right now, I can just get rid of that and put back my control force over here. Okay, so let's turn off gravity and aerodynamic drag just for a second and see how the system behaves. I'll give it some initial condition. Let's say it's offset 1 meter in the x direction, and it also just starts at rest. That's fine. And we have our plots here. So let's run this section. Oh wait, do I have KD turned on? Yeah, okay. Let me set KD equals 0. So this is with just proportional control. So this is with KD set to 0 now. Yeah, so as expected, when you have just proportional control, you just oscillate about your desired position. And that's because there's no damping in the system, right? You'll just keep oscillating forever. Now, some natural damping forces are aerodynamic drag, right? So if I turn drag back on, then we should see some damping just because the drag kind of is always pointing in the opposite direction of the velocity. So it kind of acts like the same thing as the derivative control stuff. And yep, that's exactly what we see. We see that the aerodynamic drag kind of allows our system to decay over time and reach our desired position. And I also have some animations so we can see this. So once I have like all the positions of the system saved, so here's like the position vector at every single time step, that's what was saved in R. I can just use this command over here to animate that position vector over time. So you see how the system is oscillating. And this is with no drag, so it just keeps oscillating. Now, if I turn on my derivative control, so this basically adds much more damping to the system. You can see how the actual velocity gets damped out pretty quickly, and you reach the desired position within like 10 seconds, I'd say. Let's see how that looks. So this is basically just like the spring mass system, except there's like friction on the table with the mass, so it stops oscillating. Show you that animation again. Okay, now let's add gravity back on, since that's pretty important. So let's add actually both of our disturbance forces back in. So our aerodynamic drag as well as our gravity, and let's see what happens. So if we start out with this same initial condition, if I run the system, then you see that our position in the x direction is correct, it goes to 0. Position in the y direction goes to 0, but our position in the z direction doesn't go to x to z equals 0. It actually falls down all the way to z equals -7 and kind of hangs around there. And visually that looks like this. So our drone is in the right point on the xy plane, but it's vertically fallen down. So any guesses as to why that is? Think about proportional control when we're at the origin. Like when we're basically at the origin, what happens to the proportional control and what happens to gravity? So if I start out drone over here, like already at the origin, with just PD control, then the proportional controller is going to go like, oh, okay, you're already at the origin, so this is 0, so my FP is 0, and the derivative control is going to say, okay, you're now moving, so the actual FD force is also 0. So the control force that the system produces is 0, but there's still gravity acting on the system. So gravity actually pulls it down to over here, where there is some proportional force upwards. And actually this becomes kind of like the equilibrium point of the system. So there's gravitational force pulling it down, and the proportional force is holding it up. So if, let's say this distance over here is, we can just call that R, is the distance between the origin and over here, then this force is equal to Kp times R. And this is basically what's called a steady state error, because this is kind of like an equilibrium of the system that is not what you want it to be. And you can actually find out what R is. So R is just equal to mg over Kp, and I'm sure if you plug in our values, you'll see that -7 meter deflection. So now how do you fix something like this? So this is where the integral control term comes in. So you have Fi
equals minus ki integral r dt. And this is why I was computing and tracking the value of the integral over time. So let's say you start out over here in this equilibrium position. Then without this integral term, you'll just stay here forever because the forces are all balanced out. But if you turn this Fi on, then you can see that r isn't equal to 0. So this r dt term is going to grow over time. And once this integral term starts growing, this Fi starts growing as well. So basically, when the system is away from its equilibrium, this takes into account for that and kind of nudges it back to the desired location. So proportional gain moves you to your desired position. Derivative control damps you from any, so it takes energy away from your system so you can actually converge to that. And integral control helps you deal with disturbances in your system like gravitational forces, aerodynamic forces, and it also takes away your steady state errors. So let's implement integral control now. Be easy since we're already tracking this. We just have to add our integral term back in, and I think it was minus ki times I. And then you have to turn on ki as well. So let's say that ki equals 0.5. So now if I run the system, you see that our x position converges to 0, and our z position initially falls down, but then the integral term starts to grow, right? And then once that integral term starts growing, our Fi starts pointing upwards, and that basically takes our system back to equilibrium and moves our equilibrium to the desired position and removes any steady state error stuff that we have. And if I animate this, you can see that the drone follows kind of like this spiral path. It's a very squished spiral, but it's still kind of like a spiral. And for fun, let's just try some crazy stuff. So 3, 8, 11. These are completely random values. -2, -10, 15, and 13. So if I animate this, I think that'll probably be a better spiral to look at. Nope. But yeah, you can see that the drone kind of, initially it has some velocity, so it falls into the plane where it wants to actually converge, and then it moves to the origin. And we can, let's just turn down some stuff. So what happens if I turn down my proportional gain and my KD and stuff? It should take longer to converge. And yeah, that's what we see. You can see that slowly over time, it's going to decrease. And actually, this is probably going to take a really long time. And our Ki is not enough for it to converge. So picking these parameters isn't something you do at random. It's actually, there's techniques to pick them, because if your proportional gain is too high, then you'll have a lot of oscillations in your system, and that may be undesirable. So then you might turn up KD to kind of reduce those oscillations and damp your system out. But if you turn up KD too much, then the system is over damped and it's not as responsive. Meaning it takes too long to kind of achieve that desired attitude because it's moving so slowly. And yeah. So when you're flying around with drones and taking those amazing videos and stuff,
position control is one thing where we just wanted to move to one spot. But like, for example, if you wanted to like circle around an object or follow a specific path, well, then instead of having our desired position, velocity, and acceleration is set to zeros, we'll actually set it to some path in 3D space. So this is the path that I wanted to follow. So let me just write this on a paper. So this is R sub D equals cosine 1 over 2t sine 1 over 2t and sine 1 over 10t. So what kind of path is this in 3D space? Circular, yep. So if you look at just the XY stuff, you'll see that it traces out a circle because this is a cosine and that's a sine, so it traces out a circle. And in the Z direction, it's a sine term. So basically this path is, so the top view is that it's a spiral, kind of going around the origin at a distance of 1 meter. So this has a radius of 1. But along the z-axis, it's actually following this sine pattern. So it's something like, so it's a helix, except instead of the helix is continuously moving, it's the helix is oscillating between z equals 1 and z equals minus 1. So this is a helix. So let's see how well the drone can follow this path. So this RD, VD, AD, they all come in over here in my control force, right? So where I do R minus RD and V minus VD, and it comes in the integral term over here where I do R minus RD to solve for the integral. Let me set the control against what I had before. But let's just set the initial condition to whatever it is right now. And let's see if it works. All right, so you can see the blue line is the drone's position and stuff, and the red is the desired stuff. So red is what we want the drone to follow. So you can see that initially the drone's not doing that, and over time it starts actually following the exact trajectory that we want it to follow. And let's animate this so we can see that trajectory. And you can see that helix path that it's following right now. It should actually start moving upwards as well, because the helix path is just between z equals minus 1 and 1. You should probably zoom in over here. You can see the top view that it's the exact helix path that we want with a radius of 1. You can see it's just following that, and it's moving up and down. And you can imagine that black ball in the middle is some object that you're trying to take a photo with your drone camera and things like that. So on drones, not only do you need positional control to control the position, you actually need orientation control, because the drone has to be able to keep pointing at the object that you want to film. So there's actually two control systems going on at the exact same time, one to control the position, one to control the orientation. And they're actually not like separate control systems. They have to communicate with each other, because the way the drone is oriented affects the thrust and drag and so on like that. There's a bunch of questions in the chat. Oh, we're seeing your paper. Oh no.
I'm sorry. I've just been rambling to myself about this cool stuff the entire time. Okay, now you should be able to see MATLAB. All right. So let me go over that again. So you have, what did I do? I basically just changed this. So initially I had the desired position, velocity, and acceleration set to zeros. But now I've set it to my helical path over here, so cosine, sine, and sine. And then if I want to find the desired velocity and the acceleration, I just differentiated these functions and just threw them over here. And the way that this affects our control stuff is because over here in the F control, I have KPR minus R desired. And I have V minus V desired over here. So that's where those values come in. And for the integral term, over here, it's R minus R desired when I'm computing the integral. And here you go. Here's that plot that I was talking about. So the blue line is the drone's stuff. So the drone's actual position and the drone's actual velocity. And the red line is the drone's desired position, the one that we had the function for. And you can see that over time, the drone is actually trying to track that desired trajectory. And let me animate this again so you guys can see that. And kind of like right there, the drone starts following that helical path once it's stabilized. I'll zoom in. If I show you at top, you see the exact circle that I was talking about, right? With radius equal to 1. And you can see that helix. So any questions about what we covered today? Or things you want me to try out on the code just before we head out or something like that? Yeah, for sure. I can share the MATLAB code. I'll upload it with the announcement, I think. I can just edit the announcement and then attach the code there. So you can mess around there with yourself, try some different trajectories and things like that. All right, if there aren't any other questions, then I guess we're done for today. That's pretty much all I wanted to cover. Now you guys have some idea about this very broad topic of control systems. It's actually a massive topic. It's just as big as like CFD or stress analysis. Like control systems is a very big topic, and now you guys have experienced your first little taste of that. So thank you for all coming, and take care, stay safe. Bye-bye.